Okay, picking up where we left off with the parallax method, and you hopefully realize that the parallax method is only useful up to a certain point. Eventually the star of interest becomes so far away that even with the Earth's orbit around the Sun, there's not enough of an angle. The wiggle is just not large enough to be measured. The star of interest does not really move with respect to the background stars. It's so far away. And so in order to find out the distance to stars that are farther away than parallax can tell us, we have to use what's called spectroscopic parallax. And I wanted to remind you, show you a background page from the Hertzsprung-Russell diagram. Remember this image? These are all spectrums of stars. And notice that they're all essentially the visible light spectrum, Roy G. Biv. But notice there are little black lines. Those are those absorption lines. And it turns out that not all absorption lines, or not all stars, are equal, because even though you see the same lines showing up in all the different stars, they're not equally strong in different stars. And it has to do with the temperature of the star. So by looking at these absorption lines and seeing their strength, one can determine the temperature of the star. And that's really crucial to using the spectroscopic parallax method. So I'm going to show you how to do the first line of the table on page 4 in your student guide. Where they describe, well, first of all, when you open up the spectroscopic parallax simulator, you're going to see our Sun. Remember, it's got a luminosity of 1, it's got a temperature around 5800 Kelvin. That is our Sun. It's a main sequence star. That's the Hertzsprung-Russell diagram, and there's our Sun. And notice that the spectrum of our Sun has strong ionized metal lines. It has relatively moderate neutral metal lines, and slightly on the weak side hydrogen lines. It really does not have molecular lines. It doesn't really have helium lines or ionized helium. So that is our star. And notice that the lines are relatively broad. Now, doing this activity, you have to kind of play detective. The first line says, we want a star that's got a apparent magnitude of 6.2. So you have to type in 6.2 for your apparent magnitude. And we also want strong hydrogen lines and moderate helium lines. So you have to slide this vertical line across until you have both strong hydrogen lines and moderate helium lines. So somewhere around here, where I've got relatively strong hydrogen lines, by judging by the y-axis, and notice that the y-axis for the blue line, the helium, is pretty much moderate. And notice also they tell me I need very thin absorption lines. Now that is true of luminosity class 1, your supergiants. Main sequence stars have broad absorption lines. Supergiants have very thin absorption lines. And you can read why in the background material. But by doing all this, now I know, by looking at this distance module calculation, that my apparent magnitude is 6.2, my absolute magnitude is negative 7.4. And therefore the distance to this star is about 5,000 light years. I take that back, 5,000 parsecs. These distances are in parsecs, which kind of makes sense. So this is a supergiant, and the reason why it's got a relatively weak apparent magnitude is because it's so far away. If it was brought 10 parsecs away, we would have a magnitude of negative 7.4. That's what the absolute magnitude means. Okay, moving on. Main sequence fitting. Now this is not for an individual star, this is rather for a star cluster. A star cluster is a group of stars that were essentially born out of the same material. These are like sisters and brothers or cousins. They're born out of the same material in space, and all these stars, though they may be different temperatures and different sizes, they are all about the same age. And so the way you use the main sequence fitting is you assume that if the stars are all the same age, they would evolve, the majority of them would be main sequence stars, because most stars spend so much time on the main sequence. And so when you look at a main sequence fit, what you do is you select a cluster. So now I'm on page 5, and the example is they want us to look at which one do they want us to look at? The Pleiades cluster. So we open up the Pleiades cluster, and notice that it kind of has the same shape as our Milky Way main sequence cluster, except for it's below. And what you have to do is you have to move it up and make it fit. And what that allows you to do then is to show that for a particular star, it would have a apparent magnitude of 9.1, pretty dim, but an absolute magnitude of 3.5. Okay, meaning that it's brighter than it appears, but the reason why it appears so dim is because it's so far away. And so then it allows you to then do a little calculation. You just type in the difference. You type in your apparent magnitude value and your absolute magnitude value, and it will determine the distance, 132 parsecs away. That's why the Pleiades, these stars, appear so dim. Not because they're intrinsically dim, because they're far away. And you can do this fitting by using this the main sequence fitting tool. Okay, I think I'm going to come back and knock out the rest into part 3.